Testing, 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 testing. All right, I don't know if it's working, but I don't really care. So one of the things I've been thinking a lot about is how to improve tabular data prediction, especially by using like lots of other data, because um, I think it's pretty important for like the reality is I think most of the world, most of at least business data and a lot of valuable data is in tabular form. Um, and all like not too many of the MLPs work that well. Um, and it makes sense to me why. It's just there's generally not that much data, maybe thousands of rows. Um, I think if there was millions of rows, the MLPs would work pretty well. But one of the things that occurred to me is it's all about, um, I think it's all about what people call regularization. I think it's to me, it's a weird and bad way to understand. It's like just not a good way to think. I think you could forget the word regularization. Um, because what we care about, and this chart really helped me. So there's this paper really I think is in the right direction. Uh, the tab PFN. I mean, it's a well-known thing. It's like I don't fully understand it, but it's more along the lines of like a pre-trained neural network, and they pre-trained it on a bunch of common. Uh, I guess they call priors, but in my head it's just like heuristics. But this chart's super helpful because it shows what it's doing and then how the model. Um, so each subplot shows the combination two. Each dot represents a sample color, two synthetic data sets generated by a causal tab data prior, um, two data sets from our validation Parkinson's and left. So basically, it's just two features and the category. And I don't know if this, I think it's synthetic data, but it doesn't matter. I just want it so you can see decision boundaries on toy data set generated with scalars. So these are like a simple MLP decision boundary. um, you can see how it looks at this data and says, okay, we're making a decision. These are the decisions, whether it's red or blue, and or somewhere in between. But what becomes clear here is that there's a distribution of the data, and um, it gave me so like it's all about the data distribution and what that distribution is going to look like. That's the big, I think, thing that isn't fully solved. What the data distribution is going to look like, and um, to me, there's so much information out there because there's so many data sets that can basically give us information on what a data the future data is going to look like, what the data set distribution is going to look like. Um, because like in a traditional MLP, if you have a small data set or even like a fairly large data set, like look at this one, for example, like your problem is it's going to overfit. Like it's going to overfit because it's basically trying to predict the data. No, it's not. It's not trying to predict the right thing is the problem. It's fitting a model to the data, but that's not really what you want to be doing. What you want to be doing is fitting a model to all of the data that will ever come in. And the fitting the model is the easy part. Like that is totally solved with MLP. Um, the hard part is predicting the distribution. And in my head, it's actually like we have GANs, and you can just use those. So you have my thinking is what I want to try to build out here is a process that so one of the things that's a big the reason I like this idea so much is because this tab FPN or whatever is working really well with very simple priors, and I might not fully understand it, but either way, I think my thing will work. Um, but I think it is the right. I think it's the same thing. Basically, they're pre-programming this thing to like understand. I don't know. I don't know what the hell they're doing. But what I'm thinking about doing is I'll just create a generator that will take in, like, let's say I have a data set. I'll split it. I'll like split it in half. It'll take in one half of the data set and try to predict what the whole data set will look like, or maybe even less than half, maybe like 20% or something. I can futz around with that. But so it tries to predict the distribution of the entire data set, or you could say of more data. Um, and so like this won't work arbitrarily because it'll just like it would just collapse and start predicting one point. So what you do is you have a discriminator that also takes in half of the data or whatever the generator sees, and then it takes in the the predicted the all the predicted points or the predicted distribution. You can think of them as points, like think of them as XY points. So let's take this for example. Let's say we have half of these points. Um, the generator will take in half of those points and try to predict the other half of the points. The discriminator will take in half of those points. It'll get the real points and it'll get the fake points from the generator, and it will determine is this the real points or the fake points? In other words, is this the real distribution or the fake distribution? And I like this for various reasons, but you can change. You will be able to change the size of things, like so you could and still train it. But so the discriminator, that basically what we're going to have is a system where the discriminator is really good at determining um, what a data distribution will look like, and the generator is really good at generating what the data distribution will look like. And you could run this on, you can imagine like there's millions of tabular data sets, literally millions. So you could run it on all of these And if you design the GAN and the generator discriminator and like some sort of transformer model, um, uh, then I just think it's going to basically be memorizing all of these, what you call priors, but really it's just distributions of data. Um, and then once you have done this, I think it's trivial to, there's multiple ways you could take this information, integrate it, but the most trivial way is just you take your generator, and let's say you have a data set of like 100 that you're training on. You put those 100 inputs into it, and it creates 10 million or whatever. It creates the entire distribution, and then you train on that. And I really think that would give crazy powerful um, like that. Once you have this million, like you take 100 samples, you create your million data set, or 10 million or 10 billion or whatever. You have like a full distribute, like a distribution, and then you just fit any simple. I bet you could. My guess is you can fit like almost trivially simple MLPs um, to like really complex data. I think so much of what's going on with the lack of MLPs performing on tabular data is they're just overfitting. So it's like, well, not just overfitting. Yeah, they don't have the information to know what's overfitting and not. That's the way to phrase it. They don't have information on um, yeah, what the distribution of your data looks like. And once you give them that information through all these generated samples that are very likely going to be real, um, I think they'll work really well. Um, so I'm interested. I think I'm going to try to implement this. There's like a few things that I might need to figure out, but not really. Um, I mean, I think I have the thrust of it. Um, there's maybe some certain like tricks and hacks in order to to maybe help, like if you have a huge amount of data sets, in order to help um, the discriminator and generator kind of understand priors better. But I don't know. I think it'll work pretty well. But I'm gonna try it out. We'll see. Um, yeah, I guess I'll go ahead and get started. So I guess the first thing I need to think about is like how I'm actually. I guess there's some few limitations here. Would be like um, what size of data set this thing can take in, and like your generator and discriminator can take in and output. It's interesting because you don't really need to be able to. I guess you want to be able to output like a reasonable amount. Really, the question is not the output, but the input. I think you might even be able to just output one. Probably not. You probably want no. You need some sort of distribution probably. Really, the tricky part is you want the generator to be able to take in this huge amounts of data and output more data, because that is the limiting factor in this whole thing. I mean, the discriminator also needs to be able to input large amounts of data and then predict on larger amounts of data. But one thing that's nice about tabular data is it's so small. Like you can represent so small relative to like images or text or something for the most part. Yeah, I mean, I like this idea. The other thing that's kind of elegant about it is like, if it helps on data sets that are less than like 10,000, um, if you have data sets that are already in the millions, it's likely that you have a good understanding of the distribution. So your model is fitting well to it already. And so like MLP is already going to work good. Um, this is such a handy chart too, so you can see how different algorithms are kind of do stuff. Here's the Gaussian distribution, and you can see the decision tree, and like just intuitively, that this decision tree, this way of breaking things down, that's honestly, it's not terrible. uh, it's so jagged. It's like um, it's such a jagged distribution. With tabular data, it does, and cat boost is kind of like the same thing. It's like jagular with some jagged with some uh, basically just like Legos. It's like, if you can you put smaller Legos on this, and this would be like, you can only get like a few Legos. This is like, you have smaller Legos, and with the MLP, um, it's more like dealing with like a reminds me of one of the little slap bracelets things that can like bend and uh, nearest neighbors. But yeah, I mean, if we have this system, it would just be like, okay, whatever shape, it figures it out. It figures out, all right, what's the best shape? I see why Cat Boost is kind of wins all of the Kaggle competitions and stuff. Like, I bet tabular data just tends to be jagged like this and boxy. Like the distribution is boxy. Haskell tab FBN has some really like, it's funny that tab FBN works the best. It's like, or it's close, it's up there. It's almost like the prettier the solution, um, the better it works, which is funny. Although the Gaussian is very good looking and it doesn't seem to work that well. But it's not, yeah, Gaussian. Yeah, like distributions should be pretty. If I feel like if your model is making it ugly, like if its decision boundaries are ugly, whoops, it's probably not, its predictive ability is probably bad. Called the ugly test. What happened? That'd be a hilarious paper if you just like um, just looked at like beauty versus ugliness, and like saw how it, like an ugly versus beauty thing. I bet models that were prettier would do better. Models that looked prettier would do better. I mean, look how cool that looks. It's definitely a thing. This nearest neighbors is ugly. It's like, you just know, like, what are you doing? Like, that's not the distribution. We don't see stuff like this in the world, you know. Um, and look how ugly this is. Ask L2. So ugly. Yeah, let's create some beautiful, let's see if we can make some very pretty distributions. Although this is, I'm pretty sure this is like a fake data set anyways. Um, so I got to think about the input data, and maybe there might be some hacks too. Like let's say um, I might start with some hard limits and then like figure out just to make things simple and be like, all right, the input data is going to always be like under 1,000 rows. Um, and then I think I could probably figure out some hacks or like ways to um, give the model all of the input data, but compress it basically. So I think there's some ways to do that, but I think to start, I'm just going to keep it simple and just be like, all right, let's get 1,000 rows um, and produce 2,000 rows output. Um, and I think, a transformer model should be fine for most data sets. Um, and I think what I'll do is I'll represent I'll just encode all the tabular data into, I'll one hot code the categories. So if there's a category with like 10 different classes, that'll just go to 10 features. And then I'll just encode the rest of the data, as floats. Um, And if there's like a category with more than like 100 features or something, I'll probably just drop it to start with and then figure that out later. Um, so just drop big categories. And so I already have some system for this. So I guess there's a few other questions like when I feed it the data, like a lot of data is not sequential, but it's probably best to feed it like the data, like the first half of the data set, just in case it is sequential. I think it will probably work better. Um, what else do I need to figure out? I'll probably use like some sort of transformer, like similar type thing as a transformer. So like you can almost imagine it taking in 1,000 rows. Let's say the data set has like 10 different features. We can say it has like say it has 10 different features. It'll take in like, let's say it has 1,000 features. It's almost like taking in just an image, like 1,000 by 1,000 image, and then outputting um, 1,000 by 1,000. We'll output. Let's just say we output the same amount as we input. So we're just double. Like we'll output 1,000 of the predicted. Um, and I think the discriminator will do a good job of like taking care of a lot of stuff for us because like you might be like, oh, the generator is just going to output the exact same input of the distribution, but the discriminator will catch that like right away. So it has to output stuff. So really, we need a data set that has, if we're giving the generator 1,000, the data set needs to have at least 2,000. We'll just give the generator half the data set. We'll give it the first half of the data set. It produces the second half. We do the same thing with the discriminator. Give the first half. It produces the second half. We give it the first half. It looks at out real and fake and determines whether it's real or fake. All right, I like it. Let's go. I'm going to create another. Um, what should I call this? Mm, always like name stuff Tays something. Um, Tays. Uh, Tays tabs. That's a super lame name. I'm gonna forget. What are we? We're creating distributions basically. We're predicting distributions. So I'll think of a name later. I'm just gonna call it. Okay. Um, I always just copy like a bunch of stuff from the whatever project I was just working on. I was working on some other project, the Kaggle project. Okay. Okay, so I'm just gonna get like the basics. So I don't even know. I'm just getting a basic framework here. Okay. So here's a model that is a simple let me just look at it. We have stuff that does some masking. We don't need all that fanciness. I don't think we need this. So this is embedding each feature, which I think honestly, all right. So now we're just making a simple transformer. We don't need all this fanciness. We don't need this fanciness. Don't need this fanciness. Oh, wait a second. We might want some of this fanciness. Shoot, yeah, because we're going to have, I'm just trying to think how. We'll keep this in. We are going to pass it a data set so we can train it on multiple data, on a lot of data sets. Let's think about that for a second. So the question is, yeah. Yeah, yeah. No. I think I'm just going to set the batch size to 1,000 for the input data. So basically, we'll just train one batch at a time. Really, it's, maybe I shouldn't do that because we might, if we want to train more than one batch at a time. Let me just think. So I should really call this, it's almost a full table. I should almost call it table. It's like it's a table. It's literally a table of data. We really do need to, we should, because the table should just be 1,000. We can't train on multiple tables because they'll have different sizes. So we basically need to do batch size of 1. And by batch size of 1, yeah, we'll just keep it simple to start. And I'll call it X. So really up to 1K rows. Oh yeah. We don't know how many features. The features will vary. So we do need, every data set needs to at least have its own embedding because every data set will be its own table and it'll have its own different number of features. Yeah, so we're going to embed each feature, which is just a, man, let me think if it's wise to embed. I feel like it always works better to just embed it. It could be a small, like we'll, the D model, just small number of, and here's the data sets I'll start with. We don't need any of this. I might use that. I think I don't think we want to use an encoder. Like we want to use, we'll just use a bottleneck, I'll call it. Yeah. We're also going to have to create, so this will attend, yeah, we're going to have to attend across the batch dimension too, for sure. So this is basically attending the features across the feature dimension. So every feature will look at another one. I should rename this feature transformer, and then we'll also have a I could almost call this a, yeah. We're just attending across the columns and the rows. A feature transformer and the row transformer. It's almost like the feature transformer. I guess you could think about it as the column transformer. It attends across columns, while the row transformer will. Feature transformer, column, or row transformer. It'll be important because this row transformer is going to be the thing that looks all at the values in all the rows, and it's like, okay, I think given that we can predict some outputs. Embed features, then we'll scale it back down to 1, which it would be, and then we'll pass it out. So we need to reshape this. So let me, oops, rearrange. Just make sure, first of all, that we have this rearrange. Oops. So it'll be I'll have to rearrange and then rearrange it back. Here's how you rearrange back. Let me just think. So currently we are in. Uh-oh. This shouldn't be right. Batch features. Yeah, that's right. Dimensions. So this should be fairly simple. So, oops, what did I do here? So we'll have batch number dimensions. Then we want to go to number batch dimensions. So every batch we will shoot. We might want a few more transformers. Let's see. So now for every, it'll attend to all the values. I think that's right. I think that's what we want. And then we need to rearrange it back. Get back, get back. Batch number dimensions. Okay, so that should work. Let me just try to train because right now there's no, like, what is the loss that when it outputs it, it's just going to, so I need to get the discriminator going too. Discriminator will be interesting, but I got to go put my kid to sleep, so I'm going to go. Bye for now.